For the last lesson in this chapter here, we're going to look at a couple specific things, one of which is to compute an inverse by what's known as the adjoint or adjugate matrix. And we're also going to look at the Wronskian, which will allow us to look at a set of functions and try and extend our concept of linear independence to a set of functions. So let's get started. And again, we're going to look at this adjoint, or what's now referred to as the adjugate matrix. And the adjugate matrix or adjoint matrix is a matrix of a square matrix A, and it's denoted by the adjugate ADJ of our matrix A, and it is C transpose, where C is the matrix of cofactors, and we'll have to figure out how to create that matrix. And then we can transpose it to find this adjugate matrix. And those cofactors are computed as someCij's, and then we get a plus or a minus times the minor, and the minor here is the smaller determinant, Mij, M standing for minor here. And again, this plus or minus, we're going to have to determine what that is based on a sign chart. So let's grab a theorem that will also go along with this, particularly around finding an inverse. So this is going to be theorem 14 in our text. And it says, if A is a square matrix that is non-singular, then A inverse can be computed as 1 over the determinant of A times the adjoint matrix or adjugate matrix of A. And this should remind us a little bit of our shortcut we developed for a 2x2 determinant. What this tells us is that we can expand that idea to any size matrix. I think the practicality here, though, is not always what we would hope. Computing the adjugate matrix is not a super simple process, but it does illustrate where that particular shortcut comes from in this case. And the adjoint matrix has, adjoint or adjugate matrix has other applications beyond this. We're just using it to find an inverse for ourselves. I think the best way to work through this is by example. So let's start one. And we'll take a matrix A, 2, 3, 0, 1, 0, 1, 0, 1, 1. And again, what we're going to do here is compute each of these cofactors as we go through. So it's a minor plus or minus 1. And again, we do this by a technique similar to what we would have done if we were computing, say, a cross product or something like that. So it should feel somewhat familiar to that. The matrix C, in this case, turns out to be minus 1, minus 1, 1, minus 3, 2, minus 2, 3, minus 2, minus 3. And we'll go through and make each of those calculations, but I think seeing the result ahead of time actually helps us determine what it is that we're doing and helps us connect that idea together as we're computing each one of these cofactors. The other thing we're going to need is a sign chart to help us with the plus or minus factor that goes in front of the minor. And we do that just by generating an alternating sign chart through, in this case, the same size matrix, which is a 3 by 3, starting with plus, minus, minus, plus, minus, and then plus, minus, plus. So this helps us decide what we need to multiply each of our minors by. Again, the minor being the 2 by 2 determinant that remains when we cancel out a row or a column. So let's start making some of these calculations, and we'll denote the minor in each case with an A11 being the first element in our cofactor matrix C here. So I'm going to get a -1 out of this calculation, and we'll see how we do that. Again, we're going to cross out the first row and the first column. The 2 by 2 matrix that remains is called the minor. We take its determinant as usual. In this case, we get a -1, and then we multiply using the sign chart by a +1. So it remains -1, and we see that that's what we get as the first element in our cofactor matrix. So let's back that up. And now we have that A11 is -1. And we can continue on through the matrix, computing these cofactors by canceling out all the rows and all the columns through this process. And we want to be systematic about this, so we'll do it kind of like its own little matrix here. So we've got A21, which is going to be crossing out second row and the first column again. And we compute the determinant here as 1 minus 0, which is 1. But then we use our sign chart, noting that here's our 3, the number that gets double crossed, and that position is a negative. So we have to multiply our determinant by -1. And again, we end up with a -1 for that value. So A21 is -1. Let's do A31. So we'll cross out third column, first row. The multiplier here, the position is down here in position 3,1. That corresponds to multiplication by a +1. Again, the determinant is going to be computed as 1 minus 0, which is 1 times +1 is 1. And we see that that's the value that we have in our cofactor matrix. So 1. So now let's go down the next column here. So we'll take A12, A22, and A32, and make each of these calculations. So here we're going to cross out the second column and progressively work our way down each of the 3 rows. So if I cross out the first row, then this ends up being the product here, the determinant rather, is 3 minus 0, so it's 3. We look at this particular position, also the same as this position here, 1, 2, it's a -1. So we take our determinant, which was 3 times -1, and get a -3. Again, we can see the corresponding value here in the actual matrix that's going to result. So now we do second row, second column. Again, compute the determinant as 2. We multiply times a +1, so we end up with just 2. Again, we see that value here. And finally, compute the determinant. 2 minus 0 is 2, times -1 is -2, and we see that there. So we just continue this process all the way through the matrix. There we go. So we had -3, 2, -2, and that gives us our cofactor matrix C. The adjugate then is the transpose of that matrix C. So the goal isn't to find C, the goal is to find C and then transpose it to get the adjugate matrix that we're after. So the final column here then that we would get would be A13, A23, and then A33. So let's make those final calculations. And now we're working down the third column. I'll cross out the first row. The determinant here that remains is 3. I multiply that times positive 1, so it's still 3. Third row, or rather third column, second row, and we end up with a determinant here of 2 times negative 1, so it's negative 2. Again, we see that value over here. And lastly, third row, third column, the determinant is negative 3, multiply times positive 1, so it's still negative 3. So our final value for our matrix C is negative 3. Again, we see that value there. So once you've computed all of these cofactors, then we throw it into this matrix up here, and that becomes C. The adjugate matrix then is computed by transposing that matrix C. So we get that the adjugate of A is going to be C transpose. So if we take the values that we have above here and just transpose that matrix, we would have minus 1, minus 3, 3, minus 1, 2, minus 2, 1, minus 2, minus 3. And that's our adjugate matrix. So now if we know the determinant, we can use that then to figure out what the inverse is. Again, the inverse of A being equal to 1 over the determinant of A times the adjugate matrix. And there you have it. That's how we can use the adjugate to compute the inverse of a matrix A, as long as it's non-singular.